To those across the pond and around the world. You're listening to Earth Changes Media Radio Hour. My name is Mitch Batress and I am your host. Welcome to all as you've reached the #1 news source for space weather and Earth science. At Earth Changes Media, we bring to you the highest authorities and brightest minds from the scientific world. All major agencies such as NASA, NOAA, ESA, Royal Observatory, U.S. Naval Observatory, and many more have been represented here on this show. The top scientific minds involved in cutting-edge research from our leading universities are also presented here, bringing you first-hand information of what is next to come. We also invite the brightest minds in the study of ancient texts and civilizations. We take a serious and concerned look at what our ancestors have passed down from generation to generation, often telling us with stunning accuracy of today's times. Never before have the two worlds of science and ancient texts joined together with such unity and precision, outlining a pathway of discovery. Well, once again, folks, welcome back and glad to have you here. I have two incredible guests tonight, and we're going to get into that in just a moment. Just very briefly, I do want to mention some of the events going on around the world and the tornadoes, over 50 tornadoes that hit the southern states, killing at least 50 people, possibly more. I'm not even sure what the latest count is. But it was devastating. We were able, Earth Changes Media was able to get a news alert out just prior to hitting, but not in, I'm talking about an hour. Not nearly enough time for any kind of warning. There was some warning, but still, it was a very difficult time. People are not usually prepared for this type of event in February, so in many ways it was unusual and very, very widespread over a great distance of capturing, I think, 4 states, so certainly our hearts go out to all those that have lost not only people but their homes and communities. We have we have an annular solar eclipse occurring tonight. I don't know what the exact time is. Maybe one of my guests might know that, but we have an annular solar eclipse, which means basically a partial eclipse where you'll see the rim of the sun sometime today. I don't have the exact time in front of me. And then on the February 21st, which is really quite of interest, is a total lunar eclipse. And some of the research does indeed show that in and around a total lunar eclipse, we may look for increased Earth-changing events. I would suggest that the tornadoes, because usually it's a 24-day window, 14 days prior to and 14 days after. So I'm keeping a close eye to see if there is indeed an escalation of Earth-changing events, i.e. earthquakes, volcanoes, and so forth. Matter of fact, 2 volcanoes erupted just yesterday, and again, with this theory based on the science of cycles, I would suggest that certainly fits the window of the two volcanoes that erupted just yesterday in in Ecuador and Chile. So again, we'll keep a very close eye on that. Now, introductions, and let's get right to my guest and what we're here for. Again, it's very, very exciting to me. First, Dr. Tom VanFlandern, former chief of the Celestial Mechanics branch of the U.S. Naval Observatory for 20 years and JPL contractor. He's also the author of Dark Matter, Missing Planets, and New Comets, which indicates evidence against the Big Bang Theory. Dr. VanFlandern is the founder of Meta Research, a scientific nonprofit corporation run by a 7-member board of directors, and he is certainly making some cutting-edge research in this area. My very special guest also, which will be joining him, is Dr. John Bradley, Director of the Institute of Geophysics and Planetary Physics, Lawrence Livermore National Laboratory. Dr. Bradley is lead researcher of the NASA project of the Stardust mission. Stardust is the first U.S. space mission dedicated solely to the exploration of a comet and the first robotic mission designed to return extraterrestrial material from outside the orbit of the moon. The Stardust spacecraft was launched on February 7th. Today's its birthday. 1999. What a coincidence. What a day to have them on. February 7, 1999, from Cape Canaveral Air Station, Florida, aboard a Delta II rocket. The primary goal of Stardust is to collect dust and carbon-based samples during its closest encounter with Comet. It's actually pronounced Vilt-2, a Swedish word. It's spelled wild, W-I-L-D, but it's pronounced Vilt, Swedish word, pronounced Vilt-2 after the name of its Swiss discoverer. Is a rendezvous scheduled to take place January 2004, after nearly 4 years of space travel. Well, it did that. Results are in, and that brings up our questions for the day. First of all, welcome, gentlemen. Dr. Tom VanFlandern, welcome.
Yes, thanks, Mitch. A pleasure to be with you again.
It's a great pleasure to have you. And Dr. John Bradley, thank you for coming on.
Thank you, Mitch.
Let's start with Dr. Bradley. If you could tell us a little bit more about Stardust, it's basically its mission, its premise, and when did the information come in where you were able to start to discern its relevance, in part differentiating comets and asteroids?
Well, as you pointed out, Mitch, the Stardust mission was the first sample return mission from beyond the giant planets. Actually, it's the first U.S. sample return mission since the Apollo program, which ended in the early 1970s. And to put it into perspective, during the Apollo program, we brought back from the moon approximately 280 kilograms of rocks, of lunar samples.
Yeah.
For the Stardust mission, we returned less than 1 milligram of material. So two radically different kinds of sample return mission. Now, you might think that the reason we brought back a small amount was perhaps we couldn't afford it, but in fact, the reason we brought back just a milligram is because there have been phenomenal advances in analytical technologies since the 1970s, and the bottom line is we really don't require much massive material anymore, given the instruments we have available today. So, as you also pointed out, this was a mission to get very primitive material from outside the giant planets, and there are a number of hypotheses on what comets are comprised of, and one of the most popular, of course, is that these contain material that was present at the very birth of the solar system. These are the original bits of dirt and gas and ices that were present in the pre-solar molecular cloud. And the theory is that comets formed at extreme heliocentric distances, and they basically accreted from all this primordial matter that was present in the very beginning. So that's one notion of comets. Another notion of comets, of course, is that some comets are very much like some outer asteroids. They are indeed very primitive bodies, but they may also contain material that formed in the inner solar system during its earliest 1 to 2 million years of formation. So we look at comets as a continuum of objects, and after looking at the Stardust sample for 2 years, we find that this particular comet appears to have a lot of material that formed in the inner solar system, and very little material that was present at the very beginning or was inherited from the current molecular cloud. So this is a bit of a surprise.
Dr. Bradley, I'm not quite sure why Stardust didn't get the notoriety that the Deep Impact mission did, but you came up with some pretty different results, although, in fairness, the Deep Impact mission has, after being over a year, has really started to turn. Their initial barrage was that there's no difference. The big blast we saw was more proof of the makeup of a comet. But since that time, they certainly have changed their tone, and the evidence is showing something quite different. Now, Dr. Bradley, in just a few sentences, first tell us what your analysis is of the Deep Impact mission and the differences. As I understand it, the Stardust is really telling a different story.
Well, yes, but it may simply be a matter of how we collected the data and the fidelity of the data we did collect. And what I mean by that is, well, Deep Impact, it's very difficult to beat a mission that has a large explosion in space. That's pretty cool. And of course it occurred on the 4th of July, which is a good day in the US to have things that go bang. But the analytical data collected from the Deep Impact mission, of course, is infrared spectroscopy collected by Spitzer. So this is the remote sensing data. In comparison, Stardust actually collected real dirt. These are actual physical samples that you can pick up in your hand and analyze using laboratory instruments. So the quality of the analytical data you get from an actual sample in a laboratory is totally different to what you infer from remote spectra. So different kinds of data and possibly different kinds of results, but the results are heavily influenced by the quality of the data and how the data was collected.
All right, now, thank you, Dr. Bradley. Dr. Tom VanFlandern, a man who's been at this for a long, long time, cutting edge, old school, been at it since the 60s, most noted in the 70s and 80s, definitely a senior scientist, has, for the most part, always challenged the concept of the differences between comets and asteroids. Then Deep Impact came, and Dr. VanFlandern wrote quite a bit on that. Dr. VanFlandern, that's one thing that both of you certainly agree on, is that, just in a general term, that asteroids and comets are more alike than different. Let me get you to pick it up from there.
Yes, that's certainly true, Mitch. The value of models in science is their ability to predict new phenomena, as well as to help us understand phenomena we already know about. And the models that Dr. Bradley mentioned have not had a good record of successful predictions forward, whereas the model he didn't mention, the exploded planet hypothesis, has been dead on in just about every major prediction over the last 30 years. And in particular, it indicates that both comets and asteroids basically have an identical origin. Certain classes of asteroids and all comets originated in the explosion of a body in the solar system in astronomically relatively recent times, and therefore that comets and asteroids are physically and chemically identical, except for the differences that result from their different environments. Asteroids, having remained relatively close to the sun, have had their gas and dust baked away by solar radiation pressure, solar heat, whereas comets have mostly been ejected to greater distances and are only recently come back to the vicinity of the sun and have not had nearly as much time to have volatiles baked away. But basically both of them consist of nuclei surrounded by a debris cloud where the gravitational field will support one, where it doesn't, as in the case of asteroid Eros, because of its very irregular shape. Then all of the substantial size fragments that would ordinarily be in a debris cloud would be either have escaped or have made gentle impacts on the surface accompanied by roll marks. And we now know that as just as we predicted in Science magazine and in the compendium volume Asteroids 1, that satellites of asteroids are numerous and commonplace, and now 3 comets have shown evidence of substantial satellite accompaniment as well. Then we expect that these, because of their origin in an inner solar system body, a planet-like body that exploded, we expect that they're going to contain elements that are well processed and require high formation temperatures, and we expect that comets are going to have a nucleus, but the nucleus is basically an asteroid, but it's not necessarily containing even the majority of the mass in the coma, and the coma around the nucleus is the debris cloud that was there from the original explosion, captured by the by the nucleus, but is not from the nucleus at all. So it's a very different model, but one that fits the data so much better than the others, and both the deep impact mission, which fulfilled all but one of the predictions we made in print in advance, the impact flash, dust on the regolith, the no new jet, no lasting effect on the comet, a planet or moon-like composition, and a nucleus very similar to an asteroid. I say all but one because the one prediction that's probably most distinguishing is the size of the impact crater, which we expect to be small with respect to the very solid nucleus, but obviously there's a thick dust regolith, and one makes a large crater in the dust. Well, that's the results of that prediction are still considered ambiguous, and a new mission is going to return to Comet Temple 1 in a few years and look again at the comet's surface where the impact occurred. We couldn't see it at the time because of all the dust blown out, but look and see just what kind of effect that impact had on it.
Okay. Thank you, Tom. Folks, for those of you just tuning in, you're listening to the comments from Dr. Tom VanFlandern, former chief of the Celestial Mechanics branch of the U.S. Naval Observatory for 20 years and JPL contractor. We were talking about the Stardust mission. Is there a difference between comets and asteroids? And indications are showing that there are more similarities than differences. And Dr. VanFlandern's hypothesis is suggesting that there is no difference, that comets are asteroids, simply outgassed. In other words, asteroids are outgassed comets. Dr. Bradley, does part of the research that you've analyzed from Stardust suggest instead of an outside-in Kuiper belt and so forth and formation from outside the solar system, say, could it not be an inside-out cause of splintering of asteroids and comets?
So, actually, I must admit I'm not intimately familiar with the exploding planet hypothesis, which definitely sounds intriguing. And the sample return mission from Stardust really can't speak to that hypothesis in great detail, except I can make the informal observation that the mineralogy and petrology of the return sample from Belt 2 makes it pretty clear that these are highly unequilibrated assemblages, and therefore it's highly unlikely they were ever components of a large body. So I guess what I'm saying is, despite the complications or the unexpected results from the Stardust mission, one thing is abundantly clear, that the constituent minerals have never been in a large object that's undergone, for example, parent body processes like thermal metamorphism and aqueous alteration. As for the difference between comets and asteroids, I think, yeah, I mean, we historically historically we've had a relatively naive view and a very humanistic view. The asteroids are here and the comets are there, therefore they're completely unrelated. Now, in some cases that's clearly true. If you do reflectance spectroscopy on the asteroids, we see a considerable diversity in spectral reflectance properties. So we know there's considerable diversity among the asteroids. And also we know there are asteroids in places where you wouldn't expect them. So, for example, Deimos, the moon, one of the moons of Jupiter, is in fact probably captured the asteroid. So we know the early system was something of a pinball environment with things moving around. But I think it's fair to say that there is a fundamental difference between some comets and some asteroids. On the other hand, clearly some comets and other comets and asteroids are very, very similar, as evidenced by recent data from the asteroid belt showing some asteroids, icy asteroids, actually exhibiting comae, which are clearly the classical properties of comets. So I think, what we're looking at here is a continuum in properties
Yes.
from the asteroid belt out into the Kuiper belt.
Well said, Dr. Bradley, and I'm going to key in on the word you used, continuum. We could not have this conversation as early as 1 year ago, much less 10 years ago. The science community, as I was involved in doing just what I'm doing today, interviewing the top researchers, I couldn't find anybody in mainstream that would support a hypothesis that there were any similarities between comets and asteroids. None. Apples and oranges. And look where we are today.
Well, this is good. Someone once commented the problem with science is it's performed by humans, and our human emotions, get involved in our scientific procedures. But at the end of the day, this is about a quest for the truth, and good data is what enables us to get to the truth. So thinking evolves, and this is a good thing.
Well said, Dr. VanFlandern. I'm sure you would agree on that. And yes, there is the human component, and ego can be a very healthy thing, but sometimes it can get in our ways. And look, I'm not above reproach by any means when somebody challenges my Sun-Earth connection. I get just as defensive as anybody. But Dr. VanFlandern, some words on this?
Well, I think the substance of the point that Dr. Bradley brought up was that he thought that comets could never have been part of a larger parent body, but I don't think that the evidence really supports that. Dust from Cometville 2 contains magnesium, olivine, calcium, aluminum, titanium. These are high formation temperature minerals, usually associated with volcanic outputs from deep inside planets. And to account for all these things, the standard model is hard-pressed, but now we're getting such exotic explanations as bipolar jets from the early sun shot to the outer reaches of the solar system to enrich the outer portions with hot minerals. This is a bit of a stretch. The simple explanation is the hypothesis that predicted this a generation before any of this was discovered should be given credit for the success of the model, and should really be given a lot more consideration than it's now getting in the mainstream, just because it has a long history of being batted around and has implications in other areas of astronomy where a lot of researchers are just reluctant to go. Too many careers are impacted, if you will. So there's a lot of peer pressure. I can vouch for the presence of that peer pressure in the field very definitely from personal experience. But when it's supposed to be objective and dispassionate and put controls on all experiments so that one's own biases don't influence the outcome, and that's why all our predictions were made in print well in advance and not changed or rationalized after the fact, and they've been spot on. I would point out, in addition to the ones I've already mentioned, the idea that the coma of comets is a debris cloud and not ejected from the nucleus was used to make predictions of meteor storms associated with the Leonids and with outbursts of comets since then.
Yeah.
And it was right on. It gave by far the best predictions of all of the atmosphere, and there were a great many of them that tried.
That is a good point, Dr. Bradley. You know, of the numerous meteor showers that we have throughout the year, the predictable ones, are all associated with comets. What is the general understanding of where these meteors came from?
Well, yes, there are meteor showers associated with comets, and of course, you know, the Earth periodically passes through the debris trail of comets. So there's no question that meteor showers are associated with specific comets. For example, in the last 2 years, we attempted to collect interplanetary dust particles in the stratosphere from the Greek scalar meteor stream. So these particles we collect in the stratosphere are actually samples of comets, or at least we believe them to be. And one of the interesting things coming out of Stardust, which we've done in our recent science paper, is we compared these so-called cometary particles in the stratosphere with samples collected by the Stardust mission. And it turns out they don't look anything like one another, which is, you know, again, it's one of the big surprises in science, and we're now scratching our head about the origin of these so-called cometary particles, and whether they are in fact cometary particles, or whether there are some asteroids that would give off material that's the same as comets.
Folks, for those of you just tuning in, you're listening to an interview with Dr. John Bradley, Director of the Institute of Geophysics and Planetary Physics, Lawrence Livermore National Laboratory, and Dr. Tom VanFlandern, former Chief of the Celestial Mechanics Branch of the U.S. Naval Observatory, 20 years JPL contractor, author of Dark Matter, Missing Planets, and New Comets. Dr. Bradley, I'm going to pose this question to you. Actually, it's a write-up from Dr. Don Brownlee. So let me just read this and get your comments on it. This is from Dr. Don Brownlee. Stardust samples to cometary interplanet dust particles, IDPs. The team found that 2 silicate materials normally found in cometary IDPs, together with other primitive materials, include pre-solar stardust grains from other stars, have not been found in the abundances that might be expected in a Kuiper Belt comet-like Wilt 2. What is that telling us?
Well, it's going back to my original comments at the beginning, where we expected, you know, one expectation was that the comet Wilt 2 would be a so-called mother lode of pre-solar stardust. You know, as I said, that would have been sitting at the edge of the solar nebula at the very beginning and have been frozen into cometary bodies. So we haven't found that. In fact, the abundance of these pre-solar stardust grains from other stars is orders of magnitude less than what we find in these particles collected in the stratosphere. And again, this suggests that comet Wilt 2 is not composed predominantly of outer solar system materials, that is, materials indigenous to the solar system at the very beginning. Your other guess is absolutely right. In the Stardust sample, we've found high-temperature refractory minerals, which gave rise to popular quotation of the press of fire and ice. Now, these minerals are rich in magnesium and calcium and aluminum and titanium, but they don't require a large body to generate them. So, for example, in the solar nebula, these minerals were produced in abundance, very close to the parent star at about 0.3 AU. And these so-called refractory mineral assemblages, or also known as calcium-aluminum inclusions, actually formed by vapor phase condensation from very hot vapors, where you get the condensation of first the highly refractory minerals, and as the temperatures dropped and the composition of the gas changed, you started to get lower temperature minerals progressively falling out. So there are very, very hot components in the Stardust sample. These almost certainly formed very close to the parent star, and then they were transported out by one of many proposed mechanisms. For example, the so-called X-winds or turbulent diffusion. And I think what the Stardust mission is telling us is very important. It's telling us that the early solar nebula was far more dynamic and perhaps even more violent than we expected.
Oh, that's interesting. Those are some pretty hot buzzwords. I immediately think of Velikovsky. But hold it right there. We have to take a quick break. Dr. VanFlandern, Dr. Bradley, if you could hold on for just a minute. Have to take a commercial break, and we'll be right back with part 2 and the conclusion of this interview. Folks, this is tremendous stuff, and I know that most of you realize the value of what we're hearing right now. I know I certainly do. So stand by. We'll be right back as we have to take a pause for the cause. Welcome back. For those of you just tuning in, you're listening to Earth Changes Media Radio Hour. My two special guests tonight are Dr. Tom VanFlandern, former chief of the Celestial Mechanics branch of the U.S. Naval Observatory for 20 years. What would he be called? CEO of Meta Research, or perhaps chairman, I suppose, which is a nonprofit corporation run by a 7-member board of directors, which is into cutting-edge research. As you can tell, Dr. VanFlandern has been around for a long, long time, noted as a senior scientist going back to the 60s and 70s, and certainly has kept up on all modern research. Dr. John Bradley, Director, Institute of Geophysics and Planetary Physics, Lawrence Livermore National Laboratory. Dr. Bradley is lead researcher of the NASA Stardust mission. Stardust is the first U.S. space mission dedicated solely to the exploration of a comet. And that's where we are now at the bottom of the hour. Dr. Bradley mentioned that the nebula was most likely a very violent place. Well, if that's true, there are some who believe that our solar system at one time was a very violent place. And the question is, if in fact it was at one time, could it be again? I think I'll pitch this one to Dr. VanFlandern first, and then I want to hear Dr. Bradley's comments as well. Dr. VanFlandern?
Well, I think one of the things that I would point to is one of the Stardust results is that calcium aluminum inclusions, or CAIs for short, are also found in these samples, and those are from some of the highest temperature, formation temperature. They require that high formation temperature more than practically anything else we see going around the solar system today. So it would again be a stretch on a stretch to postulate that those were introduced in the outer solar system because of the nature of the objects and the fact they have to be added on at a later epoch, and they're substantial in size, so they're not going to be driven out by just passive processes to the outer solar system. In fact, all the operating forces would tend to be just the opposite for bodies that large. Drag in the nebula would tend to bring things in. So that's, I think, another problem area that helps distinguish the hypotheses. On the one hand, that comets originated from a planetary-sized body that originally had solar composition, but then did a modest amount of differentiating, versus the idea that these were all formed from very primitive materials in the early solar system, an idea that is virtually falsified now, and we now see the new continuum hypothesis coming in, which is a good and healthy thing in that that's the way science actually progresses. Instead of one idea overthrowing and replacing another, in which there's already been a lot of investment, we see that the history of science tells us, and Thomas Kuhn tells us in the Structure of Scientific Revolutions, that what actually happens is that hypotheses tend to merge, and they change from comets are the most primitive objects in the solar system to they are a continuum with asteroids is a step in the right direction toward that change, and ultimately a generation from now we'll know that comets and asteroids are pretty much the same thing as we could have known a generation ago, but it takes time for scientists collectively to change their minds about things.
Dr. Bradley, certainly a controversial topic would be anything that would include the name Velikovsky, but staying with this idea of as humans, we'd like to think everything is predictable and safe. We'd like to think that asteroids have never hit the Earth, and these craters we see, I don't know, it happened once, it could never happen again.
Right.
What are the possibilities? Well, first of all, do you believe at one point that our solar system was a violent place?
Well, okay. Controversy is a good thing in science. I mean, it's very important for the health of science, and that's what advances in science. So I think most of us have no problems with competing ideas. This is good, not bad. But returning to the first point made by our other speaker, the transport of CAIs in the early solar nebula would that it may be difficult to imagine CAIs form very close to the star being transported to the outer solar system. In fact, there is compelling theoretical and now experimental evidence for exactly this phenomenon. The theoretical evidence, there's a number of theoretical constructs for transporting material from the inner nebula to the outer nebula. The most famous one is by Frank Shu, the so-called excellent model. And there are other theoretical models. But in the last few years, we've been able to look at accretion disks around other young stars that are believed to be analogs of our own solar system, our early solar system. And in the old days, we could look at accretion disks around these stars and basically see everything. We didn't have the resolution to poke around within the accretion disks. But now we have that ability, and in fact we can probe accretion disks around other young stars with a resolution in some cases approaching 1 astronomical unit, the mean distance between the Sun and the Earth. And what we're finding there is very compelling evidence for radial transport from material formed very close into the star out to the outer regions of the disk. So clearly this is happening. We now have solid experimental evidence, and clearly it happened in the early solar system, no question about it. Now, was this a violent place? It could have been, or it could have been just a very turbulent and dynamic environment. But the bottom line, no matter how we did this, and how violent or non-violent the early solar nebula was, we now know for sure from the Stardust mission a heck of a lot of material that formed very close to the star got lofted out to the outer edges of the accretion disk. And this is really exciting new data based on hard physical samples from beyond the giant planets.
All right. I'd like to kind of go on a parallel topic with this subject, which I think is going to lend itself to the Stardust mission, and that is going back to Deep Impact, but then I also want to introduce 17P Holmes. Now, starting with the Deep Impact mission, it was Temple 1 was the surprise of what shall I call it, the dust cloud, which resembled a coma there for a bit. I can't remember the term that they use. You'll have to forgive me. Basically an outburst. And then again, we saw it with Comet 17P Holmes on a much larger scale. As I understand it, its coma was larger than the Sun, and it seemed to come out of nowhere. Dr. Bradley, let me pitch this to you first, and I want to get Dr. VanFlandern's take on this. What is it that's what is the science behind these outbursts that we witnessed with Temple 1 with the impact, and of course 17P Holmes, which I think still nobody knows exactly what happened?
So impact, of course, was a man-made plume. So
yes.
This is an explosive
yes.
ejector plume, which lofted a lot of material above the nucleus of the comet, and of course enabled some very, very nice spectroscopy to be performed. As for Holmes, put out a heck of a lot of material. And why do comets eject these materials as they approach a star? Well, clearly heating is involved, and clearly comet nuclei are complex assemblages of volatile ices, including water ice and CO2 ice and organic ices, maybe formaldehydes, and things like that. As the comet heats up, things are going to start to outgas depending on their volatilities, and with that outgassing comes the release of a tremendous amount of dust and gas into interplanetary space. So heating is clearly involved, and in some cases you get a heck of a lot more material coming off than one would have expected. For example, in the case of Holmes. Holmes is also very interesting for an unexpected reason. It appears that Holmes may have no crystalline silicates in it. So the infrared spectra suggests that it's predominantly amorphous silicates. Now, if this turns out to be true, this is a little bit of another pleasant and unexpected surprise. And
well, let me ask you, Dr. Bradley, if you were able to capture that part of that dust,
right,
what do you think you would have found?
Based on our Stardust experience, I don't think I'd make many predictions without an actual sample.
And also, what would be in contrast of what you described as outgassing from heat, that doesn't seem to fit the scenario in the timetable that was given. It was almost instant. It was a surprise to everybody. It was short-lived. Are you suggesting that is a natural occurrence that we've seen with comets before, or would you say that this...
Well, remember, some comet nuclei have a consistency of shaving cream. And, mechanically... These may be highly unstable objects. They almost certainly are highly unstable objects. And given the way they are created, they're probably extremely heterogeneous, both in terms of their volatile ices and perhaps even their solid material. So I guess you could expect anything from a comet, given that they haven't had the opportunity to equilibrate and homogenize the way a larger parent body might, for example.
Dr. VanFlandern, the same questions. I'm grouping 17P Holmes and Deep Impact only in the sense of the outburst and what we might find. I think certainly 17P has unique characteristics. What is your analysis? Let's start with 17P Holmes.
Well, what's wrong with the idea that these are the results of heating of a nucleus is that they don't occur near perihelion or as the comet is heating. They tend to occur at great distances from the sun, as with Halley and Comet Schwarzmann-Wachmann, whichever one it is that does all the regular outbursts out near Jupiter's orbit. And even Holmes had already passed perihelion, 6, 8, 10 months earlier. It was on its way out and in a cooling down phase, and of course it's had similar outbursts in the past too under the same circumstances. And the relevant circumstance seems to be that on the previous revolution, the comet had a close approach to Jupiter that lowered its perihelion distance so that it was coming slightly closer to the Sun than before. And in the exploded planet model, which says that comets are debris clouds, a nucleus surrounded by a debris cloud, that's very significant because there's always this competition between the Sun's gravity trying to hold its debris cloud and, the comet's own gravity holding the debris cloud versus the Sun's. And if you decrease the perihelion distance, the comet gets closer to the Sun. The Sun's gravity then has a stronger pull which disturbs those outer satellite orbits, the outer fragment orbits. And in the case of Comet Holmes, a few of them are redirected such that several revolutions later they collide forcefully with the nucleus and raise a terrific amount of the dust regolith that's there on the asteroid nucleus. As I say, we've seen this happen before in the comet a couple of times, and just following the change in the perihelion distance downward, and that happened again this time, just following a change in the perihelion distance downward, and that gave us what we see there. And if there are thousands or tens of thousands of these fragments in the debris cloud in orbit, there's a generous supply of them, and this can happen regularly and definitely into the future. Every time the comet gets a little bit closer to the Sun than before, but as long as it doesn't get any closer, then the debris cloud is not disturbed any more than it already has been.
Well, let me ask you this, Dr. Bradley. Is it fair to say? No. How can I put it? Is there a way you can either self-direct or maybe someone in your team help keep an open mind, and that is the approach to your study? For example, do you, Dr. Brownlee, Dr. Hope Ishii, do all of you go into it with an idea that it could be an inside-out phenomena as opposed to an outside-in? I mean, do you even approach it or consider these issues that Dr. VanFlandern brings up?
Well, Dr. VanFlandern brings up some very interesting topics that should never be dismissed. I mean, we have to consider everything. As for do we keep an open mind, well, I should tell you that there's approximately 200 people have worked on the Stardust mission since it came back, and among us there are some very strong personalities and perhaps, dare I say it, some egos. But I've yet to hear a single individual say, "I told you so." And some of our most cherished ideas about comets, including some of mine, have been flattened out by the results from this mission. So you don't survive in this field unless you have a very open mind. I think the comet sample basically tells us that you have to expect the unexpected.
Yeah.
No two comets are probably the same, and I think that there's tremendous diversity among asteroids. We know that from their reflectance properties. We also know the Kuiper belt has a wide diversity of cometary bodies. Just looking at the properties of different objects in the Kuiper belt. So I don't know. I think the focus of Stardust, we're basically prospecting.
Yes.
And we're looking at dirt. We're analysts, and
yes.
we have a very small sample from just a single comet. And I think we are uniformly reluctant to extrapolate beyond the narrow confines of those samples. It's a sample. It's not a representative sampling of the Kuiper belt, but it's a damn good start.
Yes.
So I think that's the way to look at the Stardust mission. It's another data point. Is it statistically significant in terms of the origin and properties of asteroids and comets? Clearly it's not. It's just another data point. A very interesting one, and I think what's most important about it, it's put some of our cherished ideas to the test.
Yes, yes. Dr. Bradley, what I did not know until this very moment, folks, I didn't know it until this very moment, so I guess, my fault for not researching more deeply, is that there's going to be a revisit to Temple 1. I did not know that. Let me read this to you, folks, and I want to get Dr. Bradley's comment. The Stardust next new exploration of Temple 1 mission is to fly by the comet Temple 1 on February 14, 2011, in order to obtain high-resolution images of the coma and nucleus, as well as measurements of the composite size, distribution, and flux of dust emitted into the coma. Dr. Brad, I did not know that, and what I see missing from this is the original, the first Temple 1 team. Are they going to be involved as well, or how does this work? How do you revisit a project, a mission that occurred prior?
Well, I mean, after the Stardust space capsule was jettisoned over Utah, the space bus itself was put into a mud-parking orbit. And so the vehicle itself is still, all systems are functioning and has a darn good navigation camera. And so for a relatively modest investment, the Stardust space bus can be diverted back to Temple 2 to do some high-resolution photography and other measurements. So, you know, it's sort of, it's sort of a target of opportunity. What will be seen, of course, is an open question, but given the low cost of this mission, you know, anything new that comes out of this will be indeed new and useful. I'm not sure who's involved. I'm almost certain that the original Deep Impact team will be involved to some extent. Perhaps they'll be the dominant team on this mission. And I believe, well, you may know more than me, that the mission has been finally approved. It's been on again and off again, and most recently I heard it was definitely a go.
Well, I can't confirm that, Doctor. All I can, I'm just reading this report here. It is an official report. It is from the NASA website.
Right.
So I don't know what to say other than it's been published.
Right. Well, this is good news.
Dr. VanFlandern, any comments of this, that they're going to revisit Temple 1, and it's going to be interesting to see if they do in fact use the part of the original team, because I interviewed half of them, as you might remember, Dr. VanFlandern, when it occurred. And, you know, again, as Dr. Bradley points out, egos, you know, it can be a very good thing. I mean, that's what motivates us, and that's what drives us. But the many of them were you know, pretty well set in their analysis. And then we have the Stardust project that suggests something else. It's going to be interesting to see the dynamics of how parts of the original team will take this.
Yes, certainly so. There was a lot of betting on the team before the deep impact on Comet Temple 1 as to what would be found. And as Dr. Bradley says, no one on the team was able to come away saying, "I told you so." But nonetheless, with the exception of the size of the crater made, the predictions made and published in advance from the exploded planet model were confirmed in detail by the mission. And we'll see when we get back there exactly what sort of a crater was left, both in the regolith and possibly even all the way into the solid rocky nucleus underneath. It will add very much to our body of knowledge about comets, and as Dr. Bradley says, we've only visited a very small number of comets and have a sample returned from one. So we still have a lot to learn and before we start generalizing, but some of the models, of course, it's the nature of models to generalize, and so far the only one that has not yet been embarrassed by, in one way or another, by the data coming back is the exploded planet model.
All right, Dr. Brad, we're kind of closing up here. We've just got a couple of minutes, but I do want to get this in, and I apologize if you already addressed it, and I just didn't capture it. And that is that there's a write-up here, might be by Dr. Brownlee, I'm not sure, that says NASA study finds new kind of organics in Stardust mission, and they specifically mention, I just lost it. Give me just a second. Oh, aerogel. What is aerogel?
So, aerogel is basically, the best way to describe it is as solid smoke. This is a material made out of silica. It's like a silica foam, but it's extremely low density, and even lower now. We're making air gels here at Livermore that you cannot see with the naked eye. That is, if you put a piece of silica air gel on a bench, unless you shine a green laser through the block of air gel, you won't be able to see it. So the beauty of air gel is so low density, it's like a cushion. So materials can enter the air gel at a high speed and slowly decelerate and minimize the thermal and shock damage to the sample. This was really important. We couldn't have flown Stardust without the development of air gel, because Stardust particles impacted the spacecraft at 6 kilometers per second, or 6.1 kilometers per second, 5 times the speed of a bullet. So at that velocity, you need to have something like a baseball catcher's mitt that will slow them down without destroying them. Even using the best air gel at the time, there's been significant modification of the sample, actually more than we had hoped. But nonetheless, some material got destroyed, and a lot of material looks as if it's relatively unaltered, something we really don't understand. What I'm saying is there was a tremendous variation in the degree of response to capture during the Stardust mission. But air gel, magic material, we couldn't have done this mission without it.
Okay, just one quick correction. It wasn't Don Brownlee. It was Scott Sanford from NASA's Ames Research Center.
Right.
Dr. Bradley and Dr. VanFlandern, we are coming to the end, so I just, if you have a closing statement. First, I just want to thank both of you so much for coming on. We all benefit from this. Dr. Bradley, I commend you for your ability of your delivery. In other words, putting it in ways we can understand. We've had Dr. VanFlandern on the show several times. He's always been able to do that, so I thank both of you so much. There's just a growing, I would say since the invention of the Internet, it's no longer secular in the, isolated in the sense of only scientists can understand this. We can all research this now along with you and actually understand what you're saying. It's really changed the dynamics, and it's people like you who come on shows like this that really move this along, and I think we're all better for it. So thank you again.
Thank you, Mitch, for inviting me.
Dr. VanFlandern, a closing word?
Well, thanks, Mitch, for arranging for this. The more talk we have both inside and outside the scientific community about the different ideas on the table, the better we'll be able to assess what the best interpretation of the data is, and to get our models to the point where they do make very good quantitative and qualitative predictions well in advance of the findings, and then we can say we truly understand the nature and origin of the bodies involved. The underlying competing ideas here are comets from way back at the beginning of the solar system, or are they fairly latter-day results of the explosion of well-developed bodies? And the same would apply to other stars, too. The so-called accretion disks around other stars can very well be clouds of dust and debris from explosion of planets.
All right, hold it right there, Dr. VanFlandern. We have just a quick 30 seconds. Dr. Bradley, a final comment?
Well, I think, picking up on what you said about your show is very important. These wonderful opportunities we're getting are funded by the taxpayer. And I think the scientific community has an obligation to keep the taxpayer and everyone fully informed as to what's going on. It's critical for the health of science in the United States and globally. So I thank you for giving us the opportunity to explain to those who are funding the science what we're doing with this, their investment that benefits humanity.
Well said. And again, thank both of you. Folks, we have to close her out. You just listened to an incredible one-hour interview that we could have used 3. But Dr. Tom VanFlandern, former chief of the Celestial Mechanics Branch, U.S. Naval Observatory, 20 years. Dr. John Bradley, Director, Institute of Geophysics and Planetary Physics, Lawrence Livermore National Laboratory. So thank you to all, and to all a good night. Folks, once again, it was indeed, it met my expectations, let me put it that way, and hopefully you feel the same. This is Mitch Batchers for Earth Changes Media Radio Hour, signing off.